Okay, Physics 12, this is your lesson on explosions. So continuing to work on our unit in energy and momentum. This is now a lesson looking at specifically explosions. Okay, so we'll start. So in this one, right, again, the thing with explosions, they're very similar to collisions in the fact that they demonstrate the law of conservation of momentum. Okay, the thing that's different about collisions, where with collisions you've got objects that are moving towards each other or relative to one another, exploding objects always start initially at rest. You've got something that's not moving and then it explodes. Okay, so that would mean that the initial and the final momentum of an exploding object is always zero. Okay, so you're always kind of starting with your initial momentum. The sum of all those components would end up being zero, and then that can help you, knowing that the final momentum is supposed to be zero as well, that can help you find the relative velocities of different fragments. Okay, so if we kind of go back and tie this into recoil, these were the types of problems where in two-dimensional explosions, recoil problems were essentially two-dimensional explosion problems, right? Because recoil, again, started with that initial momentum of zero, okay? So same kind of thing here in explosions, where we're starting and ending with that momentum of zero, and that can help figure that out, right? So when we're solving those explosion problems, it's important to remember that the momentum prior to the explosion is equal to zero, and then the vector components must also be used to solve these problems, right? So we're going similar to what we did with collisions in two dimensions, where we would need to kind of break things up into their x and y components in order to do law of conservation momentum. We'll have to do the same in these explosion problems, okay? So because of the nature of that, we're really only going to go through one problem right now, and it's going to take a while just because we've got quite a few bits to it, but let's get into it. All right, so here's our problem. So we have a 25-gram firecracker. It explodes into three parts. A 6-gram fragment moves off at an angle of 35 degrees with the positive x-axis and a velocity of 42 meters per second. We have an 11-gram fragment that moves off at 33 meters per second at an angle of 21 degrees clockwise with the negative x-axis. What was the velocity of the third segment? Right, and we know that this firecracker is only exploding into three equal parts, so we could figure out the mass relatively easy by just subtracting 6 grams and 11 grams from 25 to get that third. All right, let's get into this. So, as mentioned, what we have to do is use our law of conservation of momentum here, okay? Meaning that all of the sum of the momentum of the three parts initially will equal to the sum of the momentum of the three parts afterwards, okay? So, here's some information that we know to start, right? We know that the total mass of our firecracker was 25 grams. But since we're going to be doing calculations with mass, we'll need to convert that to kilograms, which is 0.025 kilograms, right? We can then look at the masses of our three pieces, right? So our first mass, so we'll call it M1, was 6 grams, or the 0.06. Actually, there should be another zero in there. Sorry. 0.006 kilograms. We have the mass of the second part, which was 11 grams, so that's 0.011 kilograms. And then just subtracting the two, like the 0.011 and the 0.006, that will give us the mass of our third, which would be 0.008 kilograms. Okay, so like I said, all I did there was I just took the 25, subtracted the 6, subtracted the 11, got 8 grams, which is 0.008 kilograms. All right, so now what we need to start looking at as well is, well, what was happening after the explosion, right? So we know that the initial momentum is going to be zero. So all of these initial velocities for M1, M2, and M3 are all zero, okay? But what's happening after, right? So V prime 1. What was happening there? Well, that was heading off at a velocity of 42 meters per second, and it was 42 meters per second at an angle of 35 degrees counterclockwise to the x-axis, right? So again, if we just briefly looked at that question, right? Angle of 35 degrees with the positive x-axis. Okay, so what that's saying then, if we go to look at that, that means here's, you drew your kind of like your xy Cartesian plane, here's your positive x-axis, and it moved off at an angle of 35 degrees with that. Okay, so this is what's happening. This is where my velocity is 42 meters per second, where this is my 32 degree angle. Right? That allows us to then figure out both the x and the y components of that final velocity after the explosion occurred, right? Where this would be v prime 1x here, and then up here this would be v prime 1y, right? And these values again are just going to be solved using your basic trig, right? So if this is our right angle, then this is going to be found using cosine, right? So v prime 1x is going to equal 42 meters per second times the cosine of 32 degrees, which gives us a value of 34.4044 meters per second. Okay, I'm keeping lots of my decimal places here because technically we could put this directly into our formula, which would allow us to keep all of our values kind of stored in the calculator, okay? But I know that can get tricky for trying to write it all out, so we can still do this. And then our v1y here, we can get using sine. Right, so that would be the 42 meters per second multiplied by sine of 32 degrees, and that gives us a value of 24.0902 meters per second. Right, and both of those would be positive, right? Because we are still moving to the right and we're still moving up. So we would consider both of these still positive values, okay? Now, another piece of information we have is about the velocity of the second fragment, right? So that afterwards velocity, we were told, go back to the question, right? It says the 11-gram fragment moves off at 33 meters per second at an angle of 21 degrees clockwise with the negative x-axis. All right, so what that looks like then, again, think about drawing, sorry, that was 33 meters per second. So if we wanted to draw that one out, I'm just going to erase this for now. Okay, so we're drawing this one out here, right? Here's your Cartesian plane. Your negative x-axis is here, and it moved at an angle of 21 degrees clockwise, so moving this way. So you get this, where that's your 21 degree angle. There's the resultant vector of the 33 meters per second. And again, we can find this would be v prime 2x here, and this value here would be v prime 2y. And again, we're going to solve that using just sine and cosine. Okay, so our v prime 2x is equal to 33 meters per second multiplied by the cosine of 21 degrees. And that gives us a value of 30.8082 meters per second, but that's in a negative direction because it's moving to the left, so we'll assign that a negative value, okay? And then for the y, that's going to be 33 meters per second times the sine of 21 degrees, which will then equal a value of 11.8261 meters per second, and that's still moving up, so we'll still assign that as a positive value. Okay, so those values that I already erased from v1 x and v1y, the prime, we'll need those, and we'll need these as well. Okay, so now that we have these, we can set up our conservation of momentum equation. I know this would be a lot more ideal if it was all on the same board, but doing the best we can here. Okay, so then that allows us to set up the following, right? And again, we have to do this in component parts. We've got to do it in the x component and the y component, and then we can put that together to get the resultant. So let's start with the x component. Okay, so again, your conservation momentum here is going to be m1 v1x plus m2 v2x plus m3 v3x is equal to m1 v1 prime x plus m2 v prime 2x plus m3 v3 prime x, okay? But remember we talked about this, with explosions, our initial velocities, everything is at rest. So it doesn't matter what these masses are, they're all going to be multiplied by 0, and then 0 plus 0 plus 0 is just going to give me 0. Right, so this entire left-hand side of the equation will be 0, or you can kind of almost skip this step and go, all right, well, it's an explosion, so I know that the initial and final momentums are supposed to be 0, so I can just take this final stuff and say, well, that's supposed to be set equal to 0. Okay, and then we can start plugging in our values. So we have values here, right, 0.006. I'm going to leave off the units just for the sake of space right now, okay? And then the x component for the first masses, the first fragment, was the 24.0902. Oh, nope, that's, I'm looking at the y component one. Yeah, sorry, that was 34.4044. Okay, with the second mass, 0.011 kilograms multiplied by, and again, this one moved in to the left, so we'll give that a negative value of negative 30.8082, right? And then that was plus your third mass, which was the 0.008 times the velocity of the third fragment in the x, which we don't know. This is our variable, okay? This is the thing we need to solve for. So what we would need to do is multiply, multiply, add, bring over to the other side, and divide. Okay, so we can start. If I multiply this, I get a value of 0.206424. When I multiply this, and then I add it, I get a negative 0.33889. And then I'm left with this 0.008 v prime 3x, right? So then I can add these, well, I guess in this case subtract, and then subtract it from both sides to bring it over onto this side of the equation. So when you subtract this, you get a negative, so when you bring it over to the other side, it becomes positive. So you get 0.132468 is equal to 0.008, and then the v prime 3x. And then you're just dividing both sides by the 0.008, right? So the 0.132468 divided by 0.008, and then what you end up getting is a value of 16.55475 meters per second is equal to the velocity of our third fragment in the x component. So we'll need this for later, right? So kind of highlight that one so you've got it for later, right? So that's everything in just the x component. Now we do the exact same thing, but in the y component. All right, so same type of setup, except now everything is with a y. Oh, that's gross. All right, so y component, so everything here, everything that was once an x is now being changed to a y. All right, again, this whole thing is 0. And now we start plugging in those values again. So it's that same 0.006. This velocity of the first fragment in the y was the 24.0902. With the second one, again, the mass with the 0.011. Its velocity was still going up, so it would be a positive 11.8261. And then that's plus that mass of the third, the 0.008, multiplied by, again, the v prime 3y, which we don't know, right? Same process again, multiply, multiply, which gives us 0 equals 0.1445412 plus 0.1300871 plus the 0.008 v prime 3y. Add these together, but then subtract it from both sides. So this gives us a negative value over here of negative 0.2746283, which is equal to the 0.008 times the v prime 3y. Divide the negative 0.2746283 by 0.008, and what we get is a value of negative 34.328537.5 meters per second is our velocity of our third fragment, the component in the y. Okay, so now we have the x component and the y component, so now we can put those together to get our actual resultant velocity. Okay, so we use those values, we create, again, using our vector components method, right? We now create this wonderful little right triangle where we knew that the x component was still in a positive direction and had a value of 16.55475 meters per second. And our y component, so it would have gone, it was a negative value, negative 34.328537 meters per second. So our third fragment, if this is where the explosion occurred, went this way. Okay, so it went 16.55 meters per second in the x, and it went negative 34.328537 meters per second down in the y component. So what we can do is we can use Pythagorean theorem to just figure out, well, what is that v3 prime, right, using the component parts. So that would just be Pythagorean theorem. So the square root of the sum of these two numbers squared. Right, and you would just take that, square it, add them together, and then square root the whole thing. And that gives you a value of 38.103 meters per second. And now I'm ready to talk about Sig Figs, which at this point we are only allowed 2, right? I think, let's go back to the question. How many are we allowed? Looking at this, yeah, 25 gram firecracker, that's 2, 6.0 grams, that's 2. Yeah, so we're only allowed 2 Sig Figs here. So at this point, we'll say that its resultant velocity is 38 meters per second, but it's velocity, so it is a vector and it needs a direction, so we need to figure out what is this angle here, right? And we can find that angle just by using a nice little trig ratio of tan inverse, right? So theta is going to equal tan inverse of, again, use your absolute values here, so just use the 34.328537 divided by 16.55475, and you get a value there of 64.255. So again, 2 Sig Figs, we'll call that 64 degrees. And how you want to describe this, since everything else was talking about like from the x-axis, I would call it as 64 degrees clockwise from the positive x-axis, right? You could say that, right? If you wanted to give it in terms of like a math standard position angle, you could call it negative 64 degrees, right? Because if you're going to move this way, that's moving in a negative angle direction. So you can either call this 38 meters per second, negative 64 degrees, right? And everything being in standard position, or we can call it and describe it how the rest of it has been described as 64 degrees clockwise from the positive x-axis. Okay, and then that can be done as well. All right, so that's an explosions problem. So as you can see, that takes up quite a bit of time because you've got, in this case, we had 3 fragment components, and then we had to look at it in the x, and we had to look at it in the y, and then we had to piece everything back together, right? So it does take a bit of time with these problems. I'm not going to assign you too many to try and do here. You'll notice that this one was from your textbook, and this is what the textbook has as their solution. What they did was something just slightly different, right? They still have all those same values, but they just kind of went, okay, well, let's figure out the momentum first, and then multiply that momentum by the cosine of 35 to get it in the x and get the momentum in the y, right? But I mean, we were essentially doing that but what we did is we calculated that 42 times the cos of 35 first, and then multiplied it. Okay, so you're still getting those same values, right? If you look back to what we just did in the video there, right, we still see this value of the 0.206426, and we see this value of the negative 0.33889. All right, so there's a couple different ways you could try and take a look at it, but you get the same values. Okay, so that's all typed out there, but again, you see there's a lot of work that kind of comes into this. Okay, but yeah, it's there if you just want to look at it that way instead of having to rewatch the video. Okay, so again, I'll give you a worksheet with really only like 2 or 3 problems, because like I said, each of these problems probably takes you 10 minutes to do, so I don't want to overwork you there, but just kind of look at a couple of those explosion practice problems, and you're also at this point still working on your collisions assignment and your collisions lab. Okay, so this was the only kind of new lesson that's getting thrown at you in between still trying to get the collision stuff done, and I won't be giving you anything. Just check my notes. Yeah, I won't give you anything new in terms of a lesson until Tuesday. Okay, so from now until Tuesday, priority would be collisions assignment and the collisions lab. Okay, again, if you don't have Flash, just email me. I have a video recording of the lab that I can send you, and you can use the data that's there to complete the lab. Okay, so collisions assignment, collisions lab, and then this worksheet for the explosion stuff. And then you won't get a new lesson now until Tuesday, and that'll be on torque. Okay? All right, have at her.